Preparing, blah, 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 blah. Zoom to YouTube. Almost halfway there. Thanks for your patience, everybody. This is my boo-boo. Okay. That should come up. As soon as that comes up, I'll close this. Yeah, because that'll give us a duplicate. Okay, we're being live streamed.
Yay.
And we can now share a screen again.
To Albert. And I'll just bump forward to it.
There you go. I think that was
Okay.
your last.
Yay. Well, they wouldn't be live talks if you didn't have live screw ups, right? I mean, okay, I'm going to minimize this so I don't fill the whole corner of my screen. Okay, let's see. Where do we pick up? Okay, I just for those of you who have just joined us, as they say, I'll just gloss that in 2017, using relatively primitive equipment without much preparation at Alpaca Meadows Observatory, we got 23 pictures of the eclipsed sun and 8 or 10 pictures of the sky 8 degrees away. I then proceeded to show that this is what the picture looks like when you look at it carefully and you go like, well, where are the stars? Well, the stars are there, but you have to extract them. These were done, I used a wavelet method, but other methods we're experimenting with to take out the radial effect of the coronal light. And this is 3 different sets of exposures superimposed. So there's 0.6 of a second, 1 second, and 1.6 seconds exposures. And you can see it's fairly critical. If you look at the radii at which the corona stops being saturated, you can see it's pretty, if you goof by a factor of 2, the corona is going to be way, way out. If you, 1/10 of a second is the shortest, the most innermost circle here. And you can see that at 1/10 of a second, these stars, which are being picked up by these 1 and 1.6 second exposures, you probably wouldn't have gotten any stars at 1/10 of a second. You only would have got 1 or 2 or 3. So it's critical to have that exposure right. Okay, and then when we do a quick plate solve, we know then from where the stars in the sky are, where all the other stars will be, and then we can look very carefully to try to find them. And this is what we did. There's some 60 marked stars. The ones with the heavier circles are ones that had good enough signal noise ratio to probably be useful. And in the end, I think I seem to recall the solution is based on the 16 best stars with good signal noise ratio. So here's the guy we can blame it on. Albert Einstein. Isaac Newton realized that if light consisted of corpuscles, little hard things that were flying through space at the speed of light, and they went over the limb of the sun, Newton would have figured, or maybe did figure, that something passing just over the limb of the sun would be deflected from its original path. It would be hyperbolic orbit by 0.83 arc seconds. Well, Einstein did that, and he said, yeah, it's going to be 0.83 arc seconds. And then a few years later, he realized, oh no, wait, space-time is warped. It's going to be twice that. Well, now you have a test for Einstein's theory. because you can go out and do this in theory. You can take a picture of the sun during a total solar eclipse. And Sir Arthur Eddington realized this and proposed and got a grant to go to 2 locations and photograph the eclipsed sun to try to do this. Well, it's to make a long, well, I will not make a story long because I have like a 2-hour presentation talking about that. It's a wonderful story. It was well documented. And the net result was that they threw away the results from the big camera because the coelostat setting in the sun got warped. And so they used a little short backup 4-inch telescope and they got nice results. This was published to astronomers. The astronomer said, well, we don't know about this. He kind of fudged his numbers and threw away data. And the New York Times said, stars all askew, Einstein is right. So the newspapers won over peer review. Okay, in 1922, astronomers from Lick Observatory did the experiment right, got a good positive result. And then the professional astronomers said, this is good data, we'll accept that Einstein's right. So the deflections we're looking for are very small. If they were big, it would be a trivial experiment. The deflection at 1.75 per solar radius. Most of the stars you're going to find in any reasonable photograph are going to be, or in any image, 1.5 to 5 solar radii out. In order to do this with reasonable accuracy, you're trying to get the positions of the stars to about a 20th of an arc second.
Can I ask a question?
Yeah.
How does, I know in geometry, it would really, all the corona that's in there doing all this stuff, and so you take the star centroid, does that have an effect on geometry?
That was a question I really worried about. I took pictures I took regular star pictures. I added to it a bright center with a strong radial gradient, and then took the gradient out. Okay, now you say, well, a little fudgy there. But the answer was, as far as I could determine, unsharp masking and the wavelet methods didn't move the star images. So, I mean, what he's saying is you got this Gaussian bump of the star on some kind of slope. If you take the slope out, is the Gaussian bump still in the right place? And the answer seems to be yeah. But it's the first thing that I started to worry about when I started thinking about doing this. I'm trying to make the mouse wheel go like, okay, so here's the way the numbers work out. When you're talking about digital images, you're talking about determining with some precision displacements, 2, 3, 4 tenths of a pixel. Now, in good astrometric conditions, doing a tenth of a pixel centroid is not too difficult. But that's because you're using, typically during doing astrometry, 10 seconds or 60-second exposures, longer exposures, so that the seeing, the scintillation cancels out. Okay, on the images I took, the stars wobble all over the place with daytime seeing, right? If you've observed the sun in the daytime, you know that there's a lot of turbulence there. Now, when you freeze it with 1-second exposures, you know that the star is going to be over here and it's going to look like a duck. Then it's going to be over here. It's going to look like a hippopotamus, and then it's going to, you know, they're squirrely. So this is what my star was doing, and it's moving around by 1.5 arc seconds. And we're trying to get a tiny amount of that. So what do? You want lots and lots of stars. Okay, so these are the things that we knew we had to do in 2024. Now, what I've done is I've put up one of those completely horrible, unreadable slides. But the goals of our project are to measure this thing precisely. And secondarily, to produce a good how-to manual of all the parts necessary for other people without the localized expertise that we're assembling to do this same experiment. Basic things you're going to need is a high-quality refracting telescope, fast readout CMOS camera, a portable computer-controlled equatorial mount. The places we're going are 3, El Salto, Mexico, Fredericksburg, Texas, because our PI is in Texas, and northern New York State. And if we have multiple stations, we're going to be seeing more stars. We're going to be gathering more data. Our hope is that, cross my fingers, that we'll be able to get deflections measured to 1% accuracy. And that's based on some testing. One of the reasons for going to El Salto is it's at 8,000 feet elevation. Okay, much less seeing. The difference between the seeing that I saw here in Oregon at 600-foot elevation versus what Don saw at 6,000-foot elevation, he had much, much less turbulence. So we know that elevation, or at least good seeing, is very critical. Then we'll be able to put together hundreds of stars. Yes. Oh, let's admit Bill Thomas. Okay. So the hope is that our consortium will be able to get measurement errors on the order of 0.1%. Well, this is the square root things here, you know, the number of observations you put together, this plus and minus a square root. At some point, you run into systematics. My guess is that the systematic error is what will stop our precision. So here we go. We're going here. This is Durango. This is El Salto. This is the mountains. Okay, and hi, Aaron, you're on. So here we are zooming in a little bit closer. Again, you can see we're up there in pretty hilly country. And then there is a compound called Paradiso El Sierra. It's basically a gated community. We have a deal with them to show up with a lot of people and a lot of money. And we already have guaranteed access to this site. Okay, you can see that there's not all that many other places you could camp out up here. So I think we're lucky to have gotten that. These are, for just reference, the times and so forth, but the sun's going to be 70 degrees high in the sky. It's going to be near noon, beautifully well placed. If I can back up a couple steps. Yeah, this is the best, this little mark here represents the best possible viewing location, where it's as high as it gets and as long as it gets. These are the weather prospects, and we're here in the nice blue area down here at a 10% cloudiness. Our New York guy is out here at about a 50% chance of getting something. But okay, so now we start to look at the details. Okay, here's a 4-degree wide field. We have a number of different cameras. All of the telescopes that our consortium is working with are NP101 ISs. Really nice telescope. Aperture 100 millimeters, focal length 550 millimeters. Exquisitely good exquisitely good optics. We're using Sloan R prime filters, deep red, in other words, to minimize the sky brightness. These telescopes cover a wide field of view by design, and we have on order TeleVue's very latest, super good, guaranteed to be perfect field flattening wider field wideners. So we'll be actually working at focal lengths of 0.8 of 550 millimeters, 450 millimeters roughly. Makes this a little bit bigger sky than I've shown here. Okay, that's the size of the sun in the middle. And this is what the star field will look like from El Salto. We've got some fairly bright stars that we'd hope to get. We'll probably get a couple of bright star here. This goes down to 11th magnitude or 12th magnitude. As you can see, we can get stars to at least 10.5 and maybe 11th guaranteed. And if we get enough images, we may be able to work our way down to like 11.5 magnitude. So this is and there's a fair amount of thinking that goes into this. What is the best way to get the largest number of stars? Well, in 2017, we did not put the sun in the middle of the field. We displaced it so that we would get a whole row of, remember all the stars that I marked as star, star, star? Those were in there on purpose. We offset to include those stars, bright enough to show, give good enough signal noise ratio to get. Okay, when you think about, okay, remember that the displacements are declining radially. Okay, we have a QHY 600. This is the field here. It's a full frame 36 by 24 millimeter. The other one is a ZWO 1600, which is approximately half this size, so much smaller field. That gives us the same fields that we were looking at. We want to go with a wide field, several reasons. You get a lot of stars near the edge of the field with the wider field that are not much displaced. This gives you a better chance to get a good plate solution and use those potentially so you won't have to move off to a different field and throw away a lot of your observing time. There may be strategies that I'm hoping we'll be looking at in detail that would, in this wide field, put the sun first at one side and then at the other, so that you go out to 10 solar radii where the displacements are getting very small. But the same group of stars would be common to both plates. So there's a bunch of logistics we have not worked through yet. And I think that's why you start planning well ahead of time. So this is what, and if you take pictures from here, or if you go up to New York State, the sun is actually moved, or the moon is actually moved over significantly by almost its full diameter because of parallax. Okay, this is a modeling for the number of stars that we'll get, and you can see we're plotting magnitude versus number of stars for the we're modeling the number of stars we potentially will have in the field with the QHY 600 and the ZWO 1600. So you can see we can get, if we're lucky, if things are going well, somewhere between probably 200 and 500 stellar images. And it's a long eclipse from there. It's going to be over 4 minutes. Yes.
So why is there a big difference between those two?
A smaller field of view.
Oh,
This WO is 1600 is, I don't remember the number, 14 by 20 millimeters instead of 24 by 36. So, but this WO saves images much faster. Okay, and the QHY, it takes 4 seconds. You take a 1 second exposure and it takes, then you can't take the next one for 4 seconds. So you can get a special readout mode that will move the data over much faster. And we are considering doing that. That would require probably, taking a larger computer with insert cards and stuff like that to do that. It's an optical cable type of thing, I think. And it's not cheap. So again, this is one of the kinds of things you'd like to be able to take 1 second exposures, bing, 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 as fast as you can. You could get 4 times as much data. We are using the full moon, and tomorrow night, if the weather holds, I will be out taking pictures of the full moon with our setup, looking for the stars in the vicinity in those images. Refining our techniques for what is the best, how can we get the best signal noise ratio on those? Well, the moon has a different pattern. They come out the same, and it's considerably brighter, less bright. So when we are using the full moon as a proxy, we're not getting as much light from it as we would from the corona. It's still, if you think about it, we don't have any other fake coronas that we can stick up there in the sky. And the moon is there every month, we can play with it. And, I will show you some of the test images that we've taken with gibbous moons, simply because everybody was there. Let's get some pictures of the gibbous moon. Okay, this is dependent on which night can we meet, when can we be there? Right now, my house, my shop studio building is the staging ground for it. So I have a lot of telescopes, a lot of mounts, and a lot of cameras sitting in my shop. Don't let anybody know about that. Okay. So historically, we go back and we look, these blue things, these are Dyson's, that's the Eddington experiment. Dyson wrote the paper. These are his results. The dark curve, by the way, this is the expected displacement. The red triangles are Don Brunn's, and you can see his stuff fits very, very nicely on that curve. And then there's other astronomers, Jones and van Biesbroek, who tried to get it. For decade after decade, optical astronomers tried to do this experiment and do it well. And it's really, really hard to get good data photographically. The reason we're calling it the modern editing experiment is we're using CCD and CMOS cameras. And there's another crucial thing. All of the older experiments had to get a calibration image of those same stars without the sun. So about 4 months before the eclipse or 4 months after, you're going to take comparison shots through the same equipment with the stars in the same area of the sky, because you aren't going to be able, well, in 1919, doing the computations was done on pencil and paper and adding machines and stuff like that. They just didn't have the computational power, so they used an analog substitute, right? They got a good picture of the sky with the sun and a good picture of the sky without. Then they put those into a measuring engine. Those of you who know old-timey methods, measuring engine is basically a microscope carried on a slide with a precision screw. You look through the microscope, you center the star image, and you measure the distance and the number of turns on the micrometer. Okay, so you measure to a micron or so. The star images on photographic plates are big, sloppy, 20, 30, 40 micron blobs. And you try to say, well, that's exactly halfway. So all the astronomers back then used long focal lengths. They leave 3, 4, 5 meters. So they had long telescopes with coelostats and stuff like that. And the coelostats would get hot in the sunlight and distort. And Dyson would throw away the data because it looks so tacky. And then here's one more assessment of the signals for the stars that we're likely to be able to get versus solar radius versus the measured brightness of the background sky. So you can see that's the coronal light declining, and all the blue dots are various stars with their magnitudes written beside them. So we're looking at this stuff from, we did it in 2017. We learned a lot. How can we do it better and help everybody else to do it better? Okay, so this is part of the crew. People involved are variously professional physicists and teachers. Me on the left, Greg, can't remember his last name, Heather, who's our programmer, software person. One of her students, and this is Toby Dittrich, who's the guy who wrote the initial grants and stuff like that, and co-PI on the whole project. So here we are. Now we get down to nitty gritty, right? You got to make equipment function at night, outdoors, in the dew, with the mosquitoes, excepting, it's been a dry year. There's no mosquitoes this year. This is wonderful. So this is an MP101 scope. It's an AVX mount. We're using AVX mounts, not because they're great, but because they're inexpensive. And they work well enough because remember, we're doing short exposures. You have to be able to slew to the place. You only have to track for a few seconds. And they're light enough to lug around. So, and this is my little mobile computer hutch. I put bigger casters on because it's now rolling around on grass. The computer in there and a light. The two students have their laptops. The two students are developing the software, okay, to control the mount, control the camera. And then as we get into the next phase, they will be working on the software to reduce the data. I am taking the advantage of this shamelessly to have them teach me Python. Because it's very hard to learn a computer language without people who know about it. And you can say, hey, what am I doing here that's so stupid? It just won't. Oh, you put a tick mark after that and it works perfectly. It's like, yes, I've been banging my head against the Python wall and now I have people who will answer my stupid questions. And you know, Heather's a real pro, and these two kids are unbelievably, they pick up so fast, it's scary. I learned enough to write useful software already, so. This is how these kids work, and this is really interesting. They both, okay, a little bit about the software stack. We're using ASCOM, and we're using Alpica, which is a Python extension you can use so that ASCOM, it can be controlled by a Python code. So you put it in, now you've got an object that you can make it do things. So both kids independently wrote software to control the computer. I mean, the telescope. And both of their code worked. And then they put their ideas together and got an optimum kind of thing. They're now working on a GUI. Last I heard, the GUI's not quite right, but that's okay. They're going to get there. They've taken images and stuff like that, controlling the cameras also. And the way it works, these guys and Greg are a team. They have one of the telescopes, they have this whole camera, and they have taken it away, and they are learning how to set it up and use it. And they're really excited. So they're taking it out on clear nights and setting up and taking pictures. And just to learn astronomy, to become familiar, to turn themselves into astronomers instead of physics students, okay, to understand. So they're learning things like right ascension and declination. Now, right ascension and declination are the things that don't change, right? And altitude and azimuth are the things that do. All these things that we know as astronomers in our bones, that they are learning as physics students. Okay, well, we have a lot of physics to learn from them that we don't know. So it's a fair exchange. I have a bunch of pictures of them. The girl on the left is Alexa. She's part of another team. She and Jose, her supervisor, will be getting another of the telescopes. I don't know what the time scale is on that, but they will be taking that out and they will form another team taking images. They will be down in 2024 in El Salto as one of the teams taking images through our equipment. And, you know, this is classic backyard astronomy, on your hands and knees with a computer in front of you, messing around trying to make the telescope move by computer control. So here they are again. There's some code. They were smart. They went out and got glow in the dark. I guess they're gaming laptops. Gaming laptops are the best thing that's ever happened to astronomy because readable keyboards at night. I'm not a touch typist. I can't use a computer if I can't see the screen or I can't type. Oops. And here they are doing a little bit of work and bingo, we got the moon in the field, and the camera took a picture, and here it is on the screen. This is very, very satisfying stuff for them to be able to write this code and have it work. I've been involved doing a lot of the optics testing, which doesn't have to be done at full moon. This is inside and outside focus with the full aperture of the NP101. In 2017, I had to stop down the Genesis to about 80 millimeters to get rid of this marginal. You can see there's a little bit of spherochromatism, right? You got a bright ring on one side and a fuzzy ring on the other. We may decide at some point to get the best possible star images. We want to stop it down to like 80 millimeters, but we'll see, we'll evaluate that. because you may actually get with slightly fuzzy images, you may end up with a higher signal noise ratio. And that's 50% more light, which is 20% better signal noise ratio. So each of these things is something worth looking into.
Question,
Yes.
it's all about centroiding. So how good of a focus do you really need?
You want to be able to distinguish it against the background.
Okay.
Okay. The full width half max of these star images at best is about 2 to 2.5 pixels. It's basically diffraction limited. Amazingly good optics. The first telescope I started using, however, I said, why do the images look chromatic? They look chromatic everywhere in the field. That telescope, okay, Toby tried to do this experiment in Peru in 2020, and the telescopes were shipped to Peru and they were shipped back. They got thrown at some point, landed hard, and the collimation of the optics was off. One of the elements had moved probably. So it went back to Teleview, and Teleview reportedly will have it back to me early next week with the optics fixed. This routinely happens. People drop telescopes pretty often, and for $500, Teleview will fix your telescope. In fact, they won't just fix the out of optic, the banged up optics. They will fix everything wrong with the telescope when they get it. This is a great guarantee. What? Oh. Okay, we just let George in. Okay, and the middle one is a larger scale. I think it's overexposed, so you can't see that the images are nice and small, but they are. Okay, now you get to use suddenly an awesome $5,000 CMOS camera. You put it on and you take a picture of M81 and M82, and what's the thing look like? What's this going on? Well, there's a lot of magic going on in these things, and you got to figure out all the right settings to use. Okay, this is the wrong setting. Too much gain. Oops. When you get it right, this is from Dallas, which is not the greatest sky conditions. And you can see we have beautiful stars all over the place, and we're picking up a lot of faint stuff outside the Lagoon Nebula. When we're starting to talk about algorithms for taking back the sky background, this is practicing on my 2017 images. This is a profile through it. This is a 1/10 of a second exposure. This is a 1.6 second exposure. You can see a lot of light goes funny places inside these things. This is another field flattening technique I was messing with. This is now the full 3.7 by 2.4 degree field. And you can see we've done a nice job. This is the result of my Python program at flattening the field. I like it. I love Python. I hate Visual Studio 2017 or 2019, but anything you can do with Python, you can do with Visual Studio 2019. It just takes 4 times as long. But I'm getting better at both languages. And here's what from this image. This is a 1 second exposure, full moon. And you can see a fairly bright star and a much dimmer sky. This is because the dark subtraction routine basically puts fuzzes out the image, then subtracts it. And some of these clusters of pixels may be other star images. I don't know. This is one of the typical kinds of thing you do with the gibbous moon. Okay, the optics, I've used reflectors all my life. To be able to get the dark side of the moon and a gibbous moon is amazing to me because refractors scatter a lot less light. On the other hand, by the time the light's gone through a filter, gone down, hit a shiny CMOS camera, gone back up, hit the back side of the filter, come back down again, you have a lot of light thrown around inside of the camera system. Oops. Here's that flattened out, and here are the stars in the image. So there's a lot of stars. You know, if the corona was as bright as the gibbous moon, we'd have a lot more stars. This is like a 1 second exposure. And that's when you, what are these weird things? So every time I look at, yeah, right. It's probably very subtle dirt on the filter or something like that. You don't want to go in and clean these things. You'd rather calibrate the dirt out. And notice that some of the stars are in, you know, this is, and finally, current status, the initial proposal, a B-17 NASA proposal, we went from proposal to, I think it's called under consideration. So we're now writing a grant that will cover equipment, travel, software coding. We're in the process of testing telescopes, cameras, and mounts. We're developing the Python scripts for the telescope mounts and controlling the CMOS cameras. We're taking test images, and like I said, tomorrow night, Heather and I will be out shooting pictures of the full moon. And we're going to start to get systematic and do things like 10 1 second exposures, 10 2 second exposures, 10 half second exposures, trying to find out where our signal noise ratios get good. Still to do processing the images. First thing is processing them down and finding stars. One of the things I love about Python is that our huge, powerful libraries in AstroPy and SciPy that will, very smart astronomers have developed this code, and it's all out there for us to use, which is wonderful. We will not have to figure out how to find stars. Somebody's already written that code. And to testing the usability of our software, you can write software you can use, but now can you hand it off? Can our team of Heather and Kyle and Austin hand that over to Alexa and Jose and have them use it and have it work? Okay, then there's documentation, development of a lab manual, so that other people will be able to do this just by downloading the software and reading the instructions. Then all through next summer, we will be full up testing all of this stuff. And then in April 8th, 2024, we're going to be on top of a mountain or some desert in Texas or under the clouds in New York State, running this experiment. So that is, oh, yes. Yes, Toby flies an airplane. He loves flying the airplane so much that when we had to move the NP101s around, he flew them.
I have a question.
Yes.
Any consideration to blocking the bright inner corona?
That's an interesting question, but I suppose the answer is, why would you do that?
Just less scatter.
Um,
Coronagraph, but you just block the inner corona. It's so bright. you could possibly, you should get less scattering out in your field. Now, you wouldn't be able to move off to the side,
Yeah,
and you have a filter, I mean, not a filter.
we have a filter ahead of focus, yeah.
So you could put one on.
We could put an aluminized spot on it,
Or
yeah,
You would just take a machine, a little disc with a little finger thing to hold it,
yeah.
and put a magnet in it, and a magnet on the other side.
Yeah, it's worth thinking about. It'd be an easy experiment to
The
run.
interferon is so bright.
Yeah,
You could reduce the scatter, this and
Right.
turn off your filter back to the detector,
Right.
back to the filter.
now that light has to go somewhere, so we'll have to think
So you
about
can
that.
Make it a cone to shove it out.
Yeah,
the side.
yeah.
Well, you have to trade that off against how much data you're gonna lose. You know,
Well,
and
there's-
how many radii out do you block the corona?
Well, yeah, you
versus-
can't see any stars inside of what?
Oh, inside of at least one solar radius,
Oh,
yeah.
okay.
So, yeah.
Okay, I mean, yeah, you could
Yeah.
put a nice sharp thing that would cut it out.
Yeah, you
Um,
support it out the side. It's not that much, it's not like a coronagraph. You have to.
No,
there's
there's no star information inside that inner region.
There's not a huge amount of energy to get rid of, like there would be on a chronograph.
Almost all the energy in the corona light is in the close-in stuff. Yes,
Right.
that's
So
absolutely
it's not-
right.
It's not like a chronograph needs to get rid of the whole solar disk.
I can certainly test it with the moon.
Yeah.
And we'll also have a very interesting test in November when there's an eclipse
Yeah.
of the moon, and we'll shoot moon in and moon out, or moon on and
You
moon
may be able
off.
to pick up a lot more stars without all that scatter. So,
That is, yeah, and certainly it would be worth doing the experiment to determine how much scattering is in there. With the moon, I mean, you could just take field pictures and stuff with and without. Yeah, because, you know, the light that goes in there, it's gonna end up somewhere. And if we can effectively block it, that's an excellent suggestion.
You've been to the eclipse, you've seen how bright it is, and tried to photograph it and see what happens.
Oh,
And that's
yeah, I
what-
mean, if you're gonna
that's what
take,
the Newkirk camera was, the radially graded filters. I've made some of those with Jonathan Kern. You know, he and I made a project together.
yeah, and I mean, if I was gonna do this and I was gonna put money into it, I would like a nice radial gradient rather than perhaps,
That-
or maybe there's more danger in doing that missing, but
Well, yeah, you lose some stars out there, but bright, it's just the inner corona that's so bright. And there's also, it's an old issue of Stein telescope where if you take that filter and move it up, it is a gradient.
yeah, that's true.
It's a, not filter.
Yeah, sharp
The
edge,
mask.
right, that's
Right.
right, that's
And
right.
it blurs the edge and it makes it somewhat of that's an other option. to a
As long as you
gradient.
know you're not clipping the optical path, because you want the full aperture for every star image that you're gonna
I
measure,
wish I
right?
could tell you what issue that is, but if I had to take. a
I can-
guess,
I can
it would be
find
in
it.
the 70s.
Yeah,
And it's too, it's in there. Yeah. But yeah, think about
I'll
that.
just ask some of the guys at Sky and Telescope.
Yeah.
Hey, when did you run that article?
Well, they might search it easier than.
Well, Roger Sinnott would know, and
Yeah.
and I think he was on this morning. He'll probably post an answer by the time.
Did you get the question up to them or they asking for the question?
Oh, yes. I hope you guys online could hear. The suggestion was put an occulting disk of some sort in to block the inner coronal light, which would reduce the total amount of scattering that reached the focal plane. And the question was, or the comment was, there was something about this in Sky and Telescope many years ago. And my suggestion was, if Roger Sinnott's out there now, he can probably tell us pretty soon which issue that was in.
Yeah, it was about simulating a radially graded filter without going to the trouble of making one.
Yes, simulating a radial gradient filter without going to the trouble of
Space
actually making.
above This stuff
Yeah.
called film,
Right, because it's spaced out from the film, you're gonna have a radial,
right? simulate,
Yeah,
approximate, yeah.
probably going over time, right?
Yeah.
Yep.
yeah, that's part of
Okay,
our
well, anyway.
cycle.
Okay.
Let me know how that